Welcome to all in the next lecture that is on propositional equivalence. In the last lectures, we studied about the proposition, what is the propositions, connectives, and so now here we will study about that how two propositional propositions are the equivalent. So for the equivalence condition we need to know about two terms, that is tautology and the contradiction. So what is the tautology? A compound proposition that is always true. Compound proposition that is always true. So we have to sense here the true. No matter what the truth values of the proposition that occurs in it is called the tautology. So our all truth values are must be true. So that is the tautology. And the contradiction, if a compound proposition that is always false, it is called the contradiction. So here if we have the truth table of the tautology and the contradiction. So one example is here, if we have suppose p proposition, that is the values are true false. So if we take the negation of this, so what will be the negation of p? That is true false, then false is true. So now if we calculate p or negation of p. So what is this p or negation of p? True or false? That is true. False or true? That is true. Now if we calculate the p and negation of p, so true and false, that is false. False and true, that is false. So here we see that this all terms, all truth values are true. So it is called the tautology. And here next we see that these both values are the false. So it is called the contradiction. So like that, in any compound proposition in which our all truth values are true, so that is called the tautology. And if all truth values are false, so that is called the contradiction. Next term is contingency. So what is the contingency? A compound proposition that is neither a tautology or a contradiction is called a contingency. Means that is not completely all the truth values are true or false. Here maybe some values are true and some truth values are false. So here suppose we have this example, we have the two propositions p and q. So p q are there, so four rows should be there, that is true true, true false, false true, and false false. So we take in here the and, suppose p and q. So what is the p and q? We know that in our the p and q, that's value is true if our both propositions are true, right? Otherwise all are false. So here we see that here our the this proposition p and q, this truth values are not all true, not all false. Means true is also there, false is also there. So this type of proposition is called the contingency proposition. Clear? Next, logical equivalences. So what is the logical equivalences? Actually we can define the logical equivalence in two types. Means we can say that the compound propositions are logically equivalent. So we can verify this by the two ways. So first one is if we have suppose two compound propositions, capital p and capital q. Here we denoted capital p because capital p, this is a compound proposition in which we have the some small p small q are our the variables, right? So we have the any proposition like p implies q, or p or q, or p and q. So like that, that is or the one compound proposition. And another like in terms of p small pq, that is another compound proposition. So we say that that is a capital p and capital q. So if we have the two compound propositions p and q, so these are called the logically equivalent if the one way is if p biconditional q is a tautology. Means here you have to find the in these two propositions the biconditional between these, if we get this is the all values are true, means tautology, so we can say that these two propositions are logically equivalent. In another way, we can say that if our two propositions P and Q have the same truth values, for all combinations of truth values is a of simple propositions, so this is called the logically equivalent. So from two ways we can show that the propositions are logically equivalent, and we mostly prefer about this term, means we calculate P and Q and check that these values are same, these show the same truth values P and Q, that shows the same truth values, so we can say that these two propositions are logically equivalent. And what is the notation of this? We can denote this logically equivalence by two ways. First one is like that, this bike implies Q, or P is equivalent to Q. It means also P is equivalent Q. So we can represent the logical equivalence, means two propositions are equivalent, like P, this sign is for the logically equivalence. P is equivalence to Q. P is equivalence to 2. So we have these two notations, you can verify, use this by the for the logical equivalence. So now here we take the example that here we have the two propositions, these are the compound propositions, right? This is one compound proposition, this is another compound proposition, that is negation of P or Q, and second one is P implies Q. So we have to show that these two compound propositions are logically equivalent. So we prove this these two propositions are logically equivalent by the truth table, right? So here we make our the truth table for both these two propositions. So for this, first we need to we have two propositions P and Q, right? P and Q propositions are here, so four rows are here: true, 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 false, false, true, and false, false. So now for this, first we need to calculate negation of P. So first one column is for negation of P. So if P is this, so now what is the negation of P? True, then false, true, then it is false, negation of P, and false is true, and false is true. So like that we have these truth values of negation P. Next we need to calculate negation of P or Q, right? Negation P we have, Q we have, so we have to take the uh, truth value from negation of P or Q. And in the or case, we see that our value is true if both P, in negation of P or Q, we have that its value is false if we have both are the false. Otherwise, all values are true, right? Next, we calculate P implies Q. So P we have, Q we have, so now P implies Q. And in the case of implication, we our value of P implies Q is false if our first statement is true and second statement is false, then it is false, otherwise it is true. So we can see that here we have this is true, this is false, so this become false, and all are true, true, false, false. So these all are the true. Now see here. Here you can see that these both columns, this one and this one, have the same truth values. You it means identical. True, true, false, false, true, 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 true. So these all truth values are identical. This one and this one. So we can say that this proposition is equivalent to this propositions, right? So you can write this in your answer that since the entries in the fourth column and the last column of the table are same, so these two propositions are the logically equivalent. Clear? Next, we take the next example for this. Another example is that show that P XOR Q is equivalent to P or Q and negation of P and Q. Right? So here we use a truth table. So we make our truth table to calculate these values. First, we have the PQ2 propositions. So we have the four values of these. So now first we calculate P XOR Q. And we earlier studied about the XOR, exclusive OR. What will be the truth table of exclusive OR? So in exclusive OR table, we have the true is value is true if one of these, from both one of these is true, that is true, otherwise it is false. So here this is true and false, true, false, true. So it is value is true. If both are same, then it is false, right? Now for the next, for this compound proposition, first we need to calculate P or Q. So first we calculate P or Q. So now P or Q, and in the or connective we use we our truth value is uh, it is false if both are false, otherwise it is true. All values are true. Clear? Next, we need to calculate negation of P and Q. So when we calculate the P and Q, so in the and conjunction, in the and we we have the truth value is true if both are true, and here we need the negation of this. So true, true, true and true, this is true, but the negation of this, so it become the false. Otherwise in the and case, if we calculate P and Q, so its values are all values are true. In and case this is all values are false, but we have to take the negation, so these all will be the truth values. Clear? Next, for this whole compound propositions, we need to calculate the and between this and this. So when we use the and connective between this and this, and in the and connective, we know that if both are true, then it is true, right? Otherwise, its value, truth value is false. So now you can see here these both columns are identical. False, false, true, 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 false, false, right? These columns are identical, so we can say that this P XOR Q and this are equivalent, right? So from this, and you can write this is like that, since the entries of third column and the last columns are same, so these propositions are the logically equivalent. Clear? And here means from this you can see that we can simplify this XOR in terms of the or and negation, like that. Means these propositions have, both these propositions have the same meaning because these are the equivalent, right? So you see here that there are many different ways, right, to write some logical equivalent. Means this shows the logical equivalent, so this is also shows that logical equivalent. So we can verify, we can use many different ways, right, to represent a logical equivalence. Clear? And we use the truth table to find the equivalences of these. Clear? Okay, so now next come to the equivalence laws. So what are the equivalence laws? Actually, up till now we show the equivalence condition by the truth table. Now here we have the some laws that is called the equivalence laws. Through which through these laws we can also find that one proposition, compound proposition, is equivalent to other compound proposition. So what are these laws? First one is the idempotent laws. So idempotent laws is here P or P, this is equivalent to P. P and P, this is equivalent to P. So our these laws are for both conjunction and the disjunction, right? So next you can see that this is equivalent to this because P, we have only P proposition, so that is true, false. So when we use that true or true, that is true, false or false, that is false. So again we get the P. Clear? Next law is commutative law. So in commutative law, P or Q is equivalent to Q or P. P and Q is equivalent to Q and P. Next, we have the associative law. So in associative law, we use the three propositions P, Q, R. So our P or Q or R, this is equivalent to P or Q or R, right? Next, P and Q and R, this is equivalent to P and Q and R, right? Next law is distribution law. So what is the distribution law? In distribution law, we have P or Q and R. This is equivalent to P or Q and P or R. Similarly, the next one is P and Q or R. This is equivalent to P and Q or P and R. Clear? Next one is involution law. So what is the involution law? Means if we have one proposition P and we take the negation and again we take the negation of this, means negation of negation P, this is equivalent to P. Clear? So now show that how can we can write this is a, suppose we have, this is our P statement, that is true false, and we take first the negation of this, and what is the negation of this? True, that is false. False, then negation is true. So now next we calculate negation of negation P. So when we again take the negation, so false become true and true become false. So now we see here that these both are the equal, right, identical. So we can say that this negation of negation P is equivalent to P. So you can, like that, you can verify your all laws by the truth table. Clear? So now next one is the identity laws. What is the identity laws? P and T. Here T is represents the truth, means all values we have the truth values T, that is equivalent to P. And if we take the or, P or F, that is equivalent to P. And you can also verify this by the truth table. So here we take the one, suppose this is our the P statement, that values are true false, and we take the next one is true. True means all values are true. So now when we take the P and T, so what is P and T? T and T, that is T. False and true, that is false. So we see that here these both are the same, identical rows, true true, false false. So we can say that this P and T, this is equivalent to our P. So likely you can solve this, means by the truth table you can verify this. So now another one rule is domination laws. And what is the domination laws? P or T, this is equivalent to T. P and false, this is equivalent to false. Means P you can take any P, we have the proposition that is true or false. So when you take the true, so true or true, that is true. When you take the false, false or true, that is again true. So we get the true. Clear? Next one is the De Morgan's law. That law is most important law and used many uh, cases. So that De Morgan's law is that if we negate the P or Q, so that is expand is like that negation of P, and this this or converts into the and, right? So negation of P and negation of Q. Similarly, negation of P and Q, this is equivalent to negation of P or negation of Q. Next one is tautology. What is the tautology? Tautology means we get the all values are truth. So in earlier tautology we see that P or negation of P, this is equivalent to T, right? In tautology we see that. Next is the contradiction. If we take the negation P and negation P, so that become the false. So that is the contradiction. Next one is implication equivalence. Implication equivalence means P implies Q. This is equivalent to negation of P or Q. Means we can write this in anywhere if we need P implies Q. So we can also write this negation of P or Q because both are the equivalent. Next is biconditional equivalence. So if we have the P is biconditional Q, it means that in earlier in biconditional we told you that P and Q, sorry, P implies Q and Q implies P. That means is the P is biconditional Q. So you can verify all these laws by making the truth table, right? So here one we use here, we prove the here De Morgan's law by the truth table, and likely you can prove any law by the truth table. So here we use the logical equivalence. If we have the two statements the same value, so that is the logically equivalent. So what was our De Morgan's law? Our De Morgan's law is that negation of P or Q is equivalent to negation of P and negation of Q. So now we make the truth table here. So first, for these propositions, we need to calculate negation of P and negation of Q. PQ we have, so first we calculate the negation of P. So the negation of these values, negation of Q, negation of these values, we have this. Now, for this equivalency, first we need to calculate negation of P or Q. So first we P or Q in our or conjunction, in our or connective P or Q. So our truth value is false if both are false, otherwise it is true, and we have to take the negation, so it become the truth and other values are false. Clear? Next, we need to calculate negation of P and negation of Q. So negation of P and negation of Q. So in the and connective, we have the our truth value is true if both are these are the true, right? Otherwise it is false. So we see that this is true and these are the false. So now see here, we see here that these two columns are the equal truth values, means identical: false, 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 true, true. So we can say that these two columns are equivalent, means this is equivalent to this, so these two propositions are the equivalent. And in the you can write this is like that: since the entries in the fifth column and the last columns of the tables are the same, identical, so our these two propositions are logically equivalent. Clear? And similarly, you can prove our the next De Morgan's law, that is on the uh, negation of P and Q. This is equivalent to negation of P or negation of Q. So similarly, by the truth table, you can also prove this. Next, here we need to prove that P and negation of Q or Q equivalent to P or Q. So here, first, till now we prove our logical equivalence by the truth table. So now we study about the laws. So here we prove this equivalence propositions by our the using the laws. So how can we prove this? You can see here. First, if you suppose prove this is equivalent to this one, so first we always we start our from the left part. So our left hand side is P and negation of Q or Q. So now after this, and we have to till we have to solve this till we get the right hand side, right? So now solve this. So first we need here we use the commutative law. What is the commutative law? That this is a or Q, so we can write this Q or P and negation of Q. So first we use here the commutative law. After that, we use here the distributive law, because here we have Q or this. So what we see that we use here the distributive law, that is Q or P and Q or negation of Q. So first, for this proof, you need to know about all the laws, means you have to remember all the laws in your mind, right? Next, after this, what we can do? Here we see that this Q or negation of Q. And what is this Q or negation of Q? This is a tautology. T, Q or negation of Q. When you solve this, true or true, that is true, false or true, that true or false, that is true, false or true, that is true. So this is a tautology, and this is our law also. Q or negation of Q, this is T, tautology. Next, what is this? If any proposition here with and T, so here we use the identity. So any proposition and T, that is equal to that proposition. So now that is Q or P. So here we use our identity law. So now here what we need P or Q, and this is Q or P. So we use here the commutative again. So this become the P or Q, and we get here our the right side. Clear? So like that we can say that this proposition is equivalent to this proposition. So always you have to remember this. We have to start with the left part and end with exactly in on the right part, and where we have to write each and every step by a logical equivalence. Means if we suppose we use here the commutative law, so you have to write here the law. You use here the distributive law, so you have to write here the distributive law, right? So each and every step you have to mention the laws and use the logical laws. Clear? Okay, so now next we need here you see that in the last example we do this, right? So you think that why we interchange this, means why we use the commutative here. This one means we don't use here directly the distributive law. So why we don't use here the directly distributive law? Here first we interchange into the commutative law. So you know why did you do this step? Yeah, because why? Because our logical equivalence is specified or distribution on the right, our or distribution on the right side, not the left side. It is not specified that always the left side is always guaranteed for the distribution. Like that you can take suppose an matrix example, because you know that in the matrix multiplication it is not possible that if a is multiplied b, then it is also possible that b is multiply a, right? So matrix multiplication is not always true. So like that here if right distribution is applied, so not need is it is not necessary that left is also applied. So always if you use the distributive law, so you have to write in the right side. Clear? Okay. So now, next we have to simplify this statement by the laws, right? So how do we simplify this? Means we have this statement. Now we need to simplify this. So how can we simplify this? So obviously, for the simplification of any statement, we need to use the laws, because by only by laws we can simplify this. So now we have this. So first we have this negation of negation p and q. So which law we can use here? What is the negation? Here we use the De Morgan's law, because what is our De Morgan's law? De Morgan's law is that negation of p and q is negation of p or negation of q. So same we use here, negation of negation p, and this convert into the or negation q. So here we use the De Morgan's law, right? After that what we do here? Here we see that this is negation of negation p, and what is shows this? Here we use the involution law, because by the involution law we can write negation of negation p is equivalent to p. So we use here the involution law. Now after that you see here we have p or negation of q and p or q. So what you see here, I think this here use the distributive law. Means according to the distributive law you can write this p or negation of q and negation and q, because here p is same here, right? So we can write this p or negation of q and q. So here we use the by the distributive law we can write this. Now after this, what is negation of q and q? What is this value? So you can see here, if we have this is q and this is r, the negation of q, true, false, false, true. So what is the value of q and negation of q? Means true and false, that is false, false and true, that is false. So it is the false. So here this is the false, and this is the contradiction law also, right? So this is the false. And now p or false, which law here is again? So p or false, if we have the p is this and next is false, means all values are false, and we take the or between these p or f, true or false, true, false or false, false. So again we get this, these both are equal, means we can say that p or f is equivalent to p. So we can write it p, and here we use the directly the identity law. If you know about the, you remember the laws, right? So our p or false, this is equivalent to p. So now we see here that we simplify this this statement into our P, means this meaning, which of this is proposition meaning, that is simply the meaning that is P. Both are same, right? So like that we can we can use our propositions in many different ways. Clear? So like that we can verify this. Now we come to the next point, that prove or disprove. Means suppose you need to prove this, that P implies Q. This is the sign of equivalence, right? P implies Q is equivalent to P and negation of Q. So you have to check that this will be equivalent or not. So on the to prove this, first you have to remember this, to prove that the equivalence condition, if this is not true, so you need to prove, if this is not, so you need to prove after one counter example. You can show this, otherwise if it is true then it is always true. But if it is not true, so you have to write one counter example. So like here we can show this. If we have the two propositions, because two propositions are used here, PQ. So if we take the PQ and now we take the PQ is false true. So what is P implies Q? P implies Q means false implies T, that is T. If we take the P and negation of Q is false. So false and false, it is false. So now we see here, this P implies Q is true and this P and negation of Q is false. So both are not equal, right? It means that this is not equivalent to this. This is not equivalent to this. So if suppose in each you can make all these rows, means four rows also, but if one row is not satisfied this condition, means all values, what are the equivalence condition in your the truth table, that all truth values must be identical. But here we see that if we take this false and true, so here we see that this become true and this is false, so both are not the same, so we say that this is not equivalent to this statement. Clear how to prove this and how to prove the logical equivalence by the truth table and by the laws. So clear now. Thank you. Today's lecture is completed now. Be happy.